See, then you run into, like, you want to take a vacation somewhere where there's not going to be internet for a day, and then the streaks.
The streaks, yeah. Anyway, so back to class. So probability, the homework finish is posted. It has a couple of things, primarily from the methods that we did on Tuesday. In there, a discrete, some are using CDFs, some are using PDFs. And the book problem is just kind of state a problem. And so what I did for the homework is kind of go kind of step by step, have you do different pieces to try to follow through. And then there's some computing parts. So there's an R script associated with the homework that has you simulate, because a lot of these transformations of random variables, one for another, has an implication for what values you would see if you measured it or recorded something from it. So you can simulate under one and then transfer it to another, right? You can kind of get graphical pictures of some of the distribution. So you can use those commands there to do some of that. It gives you an idea of what it would look like and how these transformation formulas work in simulations. For reporting that on the homework, you can print out some of the graphs or include that with it. If you run it and look at the graphs, a small sketch, because often these are just kind of histograms or smaller plots. And so verbal descriptions also will work. So you can print it and include that, or look at what's there and describe what you see. Today we're going to do a little bit with moment generating functions, and then talk about order statistics, and then do some examples, and possibly do something on the computer with the simulation. But any questions before we get started? I guess this one, I wrote on here that it's due, Thursday, the 25th, which is, again, kind of an extent, a little bit later, rather than Tuesday. The point of doing that is that we have this Friday and Monday holiday, so you might be going away after this class to home or something and not coming back till Monday. And so if you want some time to ask about that during the Tuesday, Wednesday, about problems, that gives more time. We've done enough material, there's the project, there's another homework assignment, so if you want to get it done and have the time or capacity to do that, do it by Tuesday, or get most of it done, so it's not hanging over you while other things are happening. But making it due Thursday means that there should be ample time if you have questions about things like that. Right, so some transformations. We have looked at, so this is transformations with, we use the moment generating function, in a couple ways. This is in section 7.6, this discusses this. So we're looking at moment generating functions. Moment generating functions comes up in a number, comes up in the discrete chapter on discrete random variables, it comes up in the chapter on continuous random variables, and now with transformations, it is there. And so one example of the use of this is if, primarily if you're adding together a couple of random variables, and let's say the xi are Poisson random variables with some rate and lambda I in each group, and they're independent of one another. The probability density, the probability that xi equals some value, it's lambda I to the x e to the negative lambda I over x factorial, and the values that a Poisson count can take on are the non-negative integers. And if they're independent, we're adding them together. Well, what is y? What is this probability distribution? What are exactly the details of everything going on there? If they're independent, the moment generating function is the product of the two moment generating functions. And the moment generating function for an individual one, I guess let's write it right here. There's this e, for the first one is lambda 1, and then an e to the t minus 1, all up in the exponent. right? And the second one, there's an e and then a lambda 2, e to the t minus 1. So that's all up there. And so the exponents can add together. So you can get e, there's a lambda 1 plus lambda 2, e to the t minus 1 up there. And that looks like the Poisson form for the moment generating function. The range, values that y can take on are 0, 1, 2, etc. because x1 and x2 have 0 on up, and so y has the same range that a Poisson is supposed to have. And because it has that form, right, we deduce that the y, the sum of these things, is another Poisson, where you add the rates. Right? The Poissons kind of clump together different areas or different measurements that are Poisson and add them together. The total count is also still Poisson. And so there were some ways that we did things like that to get the probability distribution. So the means, the variances, the probabilities all follow this new Poisson formula. You can do that another way. I mean, if you didn't use moment generating functions, how would you know that it's still Poisson, right? Something is a Poisson random variable if, right, it has Poisson probabilities. So for our values y being 0, 1, 2, etc., if the probability that y equals one of its values is a Poisson formula all the time, then it's Poisson. Right? And so if you have these two things that are independent Poissons, right, you could look at the probability that x1 equals something and x2 equals something when these are two random variables, such that the sum of the two equals y. We want x1 plus x2 equal y. So if this one is x1, then that's going to mean that x2 is y minus x1. And then they would add up to the right total. But there's more than one way that this can happen. Right? That for different values of x1, you get the corresponding one, and for at least if y is not 0, then there's more than one way that can happen. And so the number of ways that can happen is x1 can actually go from 0 up to y in this case. Because of x1 and x2 being 0, 1, 2, and so on, that whole range works there. And so if you want to, is this a Poisson formula, right, you can work with this. Now they're independent. So the first one, there's lambda 1 to the x1 e to the negative lambda 1 over x1 factorial. And the second one is they're independent. So it's good to know that they're independent, so you can multiply. So that's lambda 2 for the second one, and then this is y minus x1, and then e to the negative lambda 2 over y minus x1 factorial. And all of this is inside the summation. And so this thing should simplify to become a Poisson probability, right, if it's really the Poisson distribution. So is it going to work out? We can pull out e to the lambda 1. So you do get this term pretty directly in there. And then we have this summation thing. And I'm leaving a little space because eventually something will go in there. There's I'm going to put the factorial down here. x1 factorial, y minus x1 factorial. There's a lambda 1 to the x1 and a lambda 2 to the y minus x1. That's just kind of rearranging and leaving some space. So it kind of looks like this in another example, this binomial theorem, this binomial equation. Right? Well, a combinor, like y choose x1. Remember that, so x1 is less than or equal to y because of that, right? If you put y factorial in here, right, and then you put 1 over y factorial here, it's starting to look like a Poisson, right? You need an e to the negative of the rate, and you need 1 over y factorial here, right? This whole thing, so you're going to get e to the negative lambda 1 plus lambda 2, and there's a y factorial. This whole thing, right, because there's a lambda 1 to a power, lambda 2 to y minus that power. This whole thing here is y choose x1. It's a binomial coefficient. And so this thing ends up being lambda 1 plus lambda 2 raised to the y power. And that's Poisson. That's a Poisson probability. Right. So you can do some of these things different ways. It ends up being the Poisson probabilities. The implication of the moment generating function things is that that's what it should be. It should be that. Okay. So there's a couple ways to show some of those things. MGFs, though, if you have the moment generating function also, is a little quicker, a little easier to do. But this is more of a direct way. But any questions about? Yeah.
I don't quite understand the final punchline step of how you did the simplification.
How did this one come out?
Yeah.
How did this whole thing become? Right? So, lambda 1 plus lambda 2 to the y. Right? If you expand all that out, right, you get lambda 1 sometimes times lambda 2 some of the times. Y is a count, is a number of times that it happens. So you can have a certain number of times that are lambda 1 and a certain number of times that are lambda 2 from expanding that. And you all together you get 2 to the y, sorry, possible terms. A number of ways that you can pick x1 of these terms that are multiplied together there to give you a lambda 1 is y choose x1. And that was this binomial expansion, binomial coefficients from a while ago. So the point of showing this, right, is, we're using this moment generating function. We go through this exercise, right, and come down and see we have a moment generating function like this. Okay, so then we conclude that it's Poisson. So what does it mean to be Poisson? It means that you have Poisson probabilities. And so at this point, if you told me this, I could just write down that the probabilities, are these, the rates raised to y, e to the negative rate here, over the y factorial, and that's my Poisson probabilities for all my values of y. If you didn't go through that moment generating function step, but I just wanted to kind of go back to the probabilities of x without using moment generating function, you should still be able to get down to those probabilities, right? And you can in this case. It's a little more work, right? It does require knowing this binomial coefficient thing, right? But it's still giving you the probabilities. So for some problems, right, you can use moment generating functions to, particularly for sums, and so on. But that's is only some. You do one problem on the assignment that's much more just a general discrete random variable, and you aggregate the categories and see how it goes. We're not going to talk about, there's something else called a probability generating function. We're going to skip that one in there. We didn't talk about probability generating functions earlier when that was introduced. We're not going to talk about it. Now, we're going to look now at order there's a bit of combinatorics, bit of thinking about how things go in this, and order statistics are a transformation of our data. So let's say we have a sample x1, x2 up to xn, and let's say that they're ID, so they're independent of each other and identically distributed. So that they all have the same probability distribution. Each of these xi's has some probability distribution f of x, cumulative distribution function, PDF, or something like that, but so they're all the same distribution. Same mean, same variance, and same probabilities for different possible outcomes. The x of the kth order statistic usually gets this little parentheses around it in here, right? It's the kth order statistic. The way this would come about is if you put the values in ascending order. Then this x of k is the kth smallest of those. So x of 1 is the first smallest, or the minimum. So x of 1 is the minimum. And then x of n is the maximum value. And they're all, sorted. Like this. And if you actually had, values, you could just put them in order and kind of get a certain, the jth or the kth particular value. But these can also be viewed as random variables. There's some different samples of size n. The smallest value is not always going to be the same. Right? There's randomness there. So there's a distribution of what is the smallest value from a sample. Right? And there's a distribution of the median and 75th percentile or the maximum, and often you're interested in those. So we're interested in these often because we're interested in, the height and weight of children, and you look at it for a certain age. The 5th percentile is pretty low, right? So if you had 10,000 children, what is the lowest 50, the lowest 500 out of those, right? You might also be interested in the upper ones. What is really high in terms of weight? Poverty, other issues of income or wealth. Where is the lowest? Where is the highest? We're interested in those type of things, and order statistics pertain to those. Right? To know the distribution of an order statistic, right, we're going to ask the question: what is the cumulative distribution function, or CDF, of a particular order statistic? What's the probability that a particular order statistic is less than or equal to some value? If we get a function for that and it's continuous, we can differentiate that and get the density function. And we can see, is it skewed to one side? And we can use that to either simulate it or just describe it. Now, a couple order statistics are easier to deal with than others. Right? The maximum is the nth order statistic. What's the probability that the nth order statistic is less than or equal to x? Let's call this maybe the nth cumulative function evaluated at some value, little parentheses here. The probability that the maximum value is less than something. 0. No, not necessarily. Right. So one way to think about these things. So x could be a very large value, right? So the maximum might be typically very much less than this, right? What's the, right, that's less than a certain value here. So if x is a value, one way to see this, these is what's the chance, so this is the maximum, is less than that value. What does that tell you about all n of the values? Can any one of those be bigger than that little x? The maximum is below a cutoff. Then every single value, x1, x2, all the way up to xn has to be less than. So the probability that x1, x2, xn all are less than or equal to x has to happen. So if our maximum is going to be less than a value, then all the random variables have to have values that are less than that. But these are independent random variables, right? So the probability of all of these things happening, right? And the probability that x1 is less than or equal to that, and the probability that x2 is less than or equal to that, all the way up to the last one. Probabilities multiply because of independence. What this is the cumulative distribution function for our random variables. It's of x1, but it had just the same x distribution as everything else. And then this one is that same cumulative distribution function for the general random variable x, evaluated at that same point, up to the last one. So the cumulative distribution function for the maximum is the cumulative distribution function of one of them raised to the nth power. That's the cumulative distribution function, CDF. So what's the density? So this is the probability that the maximum is less than or equal to a certain value when x comes from some distribution. So what is the probability density function of the maximum? Well, if the cumulative distribution function of this maximum one is the cumulative distribution function of one of them raised to the nth power, to get the density of this nth one, we differentiate. The cumulative, right? Differentiate the capital one, we differentiate it, and it becomes the lowercase one, and that's the density. So we're going to get differentiate this. It's n times the cumulative distribution function of 1, that thing raised to the n minus 1 power, and then we take the derivative of the capital in here and get the lowercase one. So that ends up being that. I just what I'm looking at. So we can look at this for certain. Yes.
Sorry, which CDF are we taking the derivative of? Is it of like x1, x2? Is it of a specific x, or is it of like the distribution that they're all following?
Right. So this one is the one that they're all following.
Okay.
Right. Here we're taking derivative of that. Right. That little f of x. Right. So each x1, x2, right, all of them have this particular distribution. We're trying to figure out is the derivative of that thing is this little density. These are the individual x's. This thing is the density, the PDF of the maximum. Let's look at a concrete example. All right, so one example, let's say x is uniform. This we get a bunch of uniform random variables. So xy is uniform. So we're going to get a bunch of uniform things, x1, x2, up to xn. And let's see, so for the density of this one, f of x is simply just 1. For 0, that's uniform constant. The cumulative distribution function, if you integrate that, ends up being x. And what does then the density of the maximum? We're going to take the maximum of all of these things. What's the probability density for the maximum? The formula says you take n times the cumulative distribution function, that thing raised to the n minus 1, times the density. That was this business here of doing that. So in this case, it's just n times, well, for 1, the cumulative here is this, n minus 1. And then this thing is just 1. That's then the density function for this one. Let's see what it looks like in simulation. Right? So if we take a bunch of, let's see, let's say we take 5, right? And we're going to take let's take 1,000 different samples, right? We're going to take 1,000 samples. So we'll do a little loop here for 1 going up to 1,000, and oops, be n, right there. What? Okay, there we go. All right, so we're going to do for 1 to 1,000. The maximum, so that maximum is going to be the maximum of random uniforms. We're going to take 5 of them, and the default, they're between 0 and 1. 5 values between 0 and 1. We're going to take the maximum. Max is not max. Our function is max. So we're going to take maximum, and we're going to save it in that maximum value. So now the maximum values, say, here's the first 10. These are the each one of those is a maximum of 5 numbers. I haven't shown you those 5 numbers, but those are uniform numbers. And so there's a distribution associated with the maximum. So if we take the histogram of the maximum values, it looks like that. Right? And so our maximum, when we're randomly picking 5 uniforms, is concentrated up there near 1. You tend to get higher than average, higher than 50% maximums when you take 5. But there's a chance our maximum is actually going to be less than 0.5. Right? If we got all 5 of our values less than 0.5, we'd get a smaller maximum. There's a chance of that. It's a small chance. We could actually what's this? How many times out of 1,000 was our maximum less than 0.5? That's divided by 1,000 simulation times. So about 2.8%. The probability is about 2.8% that we would be less than 0.5. And all 5 of our random numbers would be small. And so that's the density function for the maximum. And if you graph this function for x going from 0 to 1, is going to be follow that shape. It decreases quite a lot as x gets smaller, right? Raising it to the fourth power is going to make that much smaller. That's the density for the maximum. We could do this with a different distribution. Right? Say x has an exponential distribution. Then the density of x is 1 over theta e to the negative x over theta. The cumulative distribution function of x is 1 minus e to the negative x theta. And let's say we take n individuals. And so this is kind of the waiting time until n people finish something. Right? Who takes the longest? What's the distribution of the longest time it takes somebody? What's that distribution? Well, the cumulative distribution function f of the largest one is n times the cumulative 1 minus e to the negative x over theta, all of that raised to n minus 1 power, right, times the density, 1 over theta, e to the negative x over theta. So that's what it is. I don't recognize that as any particular distribution, right? But that's the probability density function. You probably can take expectations of that and other things, or graph it. Certainly you can do a simulation. So if we changed our simulation over here, we're going to change our simulation. Now, I'm just going to replace that maximum. So I'm going to do the same 1,000 times. Let's get the maximum value. But now instead of taking uniforms, let's take random exponentials. Let's take 5 exponentials. We have 5 people. How long is it going to take the longest one? Do it. And I think I want to put 5 here. Well, we might need to check this. So let's see. I wanted to look at what's the mean if we do a random exponential to, say, 1,000 people with a mean of 5. 0.2. So no, it's 1 over. Right, remember, there's a couple ways that this exponential can go. Some things put it as 1 over theta times e to the negative x over theta. Another way represented is theta times e to the negative x theta. So, it can be kind of 1 over. The mean that we are operating with is a mean of 5, right? So if you put it as 1 over, it will be the right one. So the exponential, remember, is just always downsloping. The density is always downsloping. If you do a histogram of these maximum values, you get something like this. It's not completely downsloping. If I do a histogram of a random sample of, say, 1,000 points from that exponential, right, the density is sloping down. Right? These are 1,000 individual values. This is the picture for 1,000 maximums. Each one's a maximum of 5 values. You're unlikely to get something that's really low, and often you get values that are a little bit higher, because one of those 5 can be very high. So that's the distribution of the maximum, and this is the formula for its density for what that's worth. How about the minimum one? Minimum of x1, x2, xn. That's the order statistic with the 1 here. So if we want the cumulative distribution function of x1, that's the probability that the minimum minimum is less than X, that means that at least one of them is less than X. Maybe they all are. It's a little bit harder to write out. So we're going to do 1 minus. The chance that the minimum is all less than or equal to X. 1 minus the probability the minimum is greater than some value. So if the minimum is above some threshold, what does that tell you about all in observations? They all got to be big, right? X1 greater than X2, with a comma, greater than X, X3 greater than X, Xn greater than X. They're independent, so you can multiply the probabilities of each of these things. What's the probability that something's greater than x1, x? Well, the chance that you're bigger is 1 minus the cumulative. So it's 1 minus the cumulative from the x distribution of x. And you get that in times. So that's a little jump there, right? But it's a probability of each one of these things multiplied together, so there's going to be a power of n. The probability that, say, the first one is greater than x is 1 minus the probability that x1 is less than or equal to x. 1 minus this cumulative. So the figuring out what the probability that one of these is bigger than x is this thing. They're identical, they're independent, so we multiply that together in times, and so it's to n power. That's the cumulative. For that one, right? So that's how. So if we differentiate it, we get the density. So what is the PDF of the first one? The density of the first one, take the derivative with respect to x of this thing, right? 1 minus f of x to the nth power. So there's an n and 1 minus f of x raised to the n minus 1, and then a derivative of that density. There's kind of a negative and then another negative, and they cancel, so that ends up being the density of the minimum. And so we're in the uniform case. This, it turns out to be, the density over here was 1 minus, that's 1 minus x and n minus 1. And that just is that. This is 1. In the exponential case, the cumulative distribution function, well, 1 minus that was just e to the negative x, and then there's n minus 1 of those. And this thing was 1 over theta e to the minus x over theta. And there has to be a theta in here. So based on the cumulatives and things, you can write down what these densities are if you're interested in that. Right? We can simulate the distribution of the minimums, right? So on a computer, the minimums, let's say the minimum, the long word minimum is a numeric, also of length, we'll do 1,000 values. And the sample size still going to be 5. And so if we, this one finally worked. We're going to do a loop, do it 1,000 times here, and say the minimum value is going to be the minimum of random uniform sample size n between 0 and 1. Right? And so that goes through for each run through that, it generates 5 values, takes the minimum of it. If we do the histogram of those minimum values, it looks like this. Right? It's kind of the flip side of the maximum, the reflection. So that's a distribution. So we get 5 random variables, we reduce it to the smallest one, and that's what the distribution looks like. So, the mean is going to be around here somewhere. As you get bigger sample sizes, right, that distribution is going to change. From our formula, we just change n in here and get a new value. So for instance, we could just simulate what if say n is 15, right? Then we're taking 1 minus x to the 14th power. So something like 0.5 to the 14th power gets pretty small. Like 1/2 to the 14th power is 1 over like 4, like 16,000, right? It's really a tiny number. So if n is something like 15, and we do the same code. So that same code will work because I just use the n in there and then close that off. Here, now the histogram of this minimum value, right, is they're really small. Right? The minimum, getting 15 values and having them all be above 0.2 is pretty rare, right? And that's reflected in that density function there. So, what is it that we're doing with this, right? So we have, kind of to review, right? We have a bunch of random variables, independent, identity distributed. We want to summarize all those by saying what's the minimum, right? And if we know the distribution of x, and we know it's CDF and PDF, and we want to analytically figure out what is the actual density function for this. Going through this argument gives a general way of solving for the cumulative, differentiating gives us the density, and then we can plug in the specific things here for whatever distribution we started with. And analytically, that's the density. That describes the distribution. Sometimes we'll simulate it, sometimes we'll work with this to figure things out. But that's a transformation from all those n variables to one single summary. The other ones, the other order statistics are a little bit more involved. Okay. So other order statistics. Besides them are a little bit more involved in the sense that you can see that the jth one, jth order statistic, out of a sample size n, we would do the same thing. One part of, I think, rationale for also looking at this, it just kind of emphasizes what the cumulative distribution means. And that as we transform things in variables into summaries, they become new random variables. So the cumulative distribution function for this one is the probability that the jth order statistic is less than or equal to x. Jth order statistic, you're going to put them all in order, and the jth order one is going to be smaller than some cutoff. So it's going to mean that at least j of the x's are less than or equal to x. little bit more complicated, right? You have to have at least j of them less than or equal to x, and the others can be bigger. And that's why the orthostatism can be there, but not higher. So to get something like that is, there's a lot of different possibilities. You can have them all. If all of them are less than x, then the jth one certainly is less than x too. Right? So we can have some j to n of them less than x. Right? And you can add up the probability that k out of n of the x's are less than or equal to x. Kind of like a binomial, right? It's a funny binomial. There's n choose k. There's a cumulative distribution from the x's raised that thing raised to the k power, and then the other ones are bigger, so it's 1 minus that. N minus k. So that's actually the cumulative distribution function. So it's a, so you go through these, thinking about the probability is what does it mean for something to be less than a value? To have a certain sample with it split up a certain way, and then put together a combinatoric probability thing. And if you want the density of the jth one, right, you're going to differentiate that thing, the jth one, with respect to x. We'll jump to the answer. There's a couple pages of derivation to go through this in the book. They kind of go through a few things. The answer, the density function for the jth order statistic turns out to be n choose j times j is the cumulative distribution function raised to the j minus 1, and 1 minus cumulative distribution function raised to the n minus j times the density. So you can look at details if you're interested into over a couple pages in the book. You just derive the result and set things up. But it has a piece that some of the observations are less than the x, and there's a probability of that. There's some that then could be bigger than that, and there's a probability associated with that. So one kind of neat result, that comes out of this. So say at one application, say the x's themselves are uniform between 0 and 1. Just getting random numbers between 0 and 1. What's the jth? What's the distribution of the jth order statistic? So when it's uniform, this is just x. The cumulative is just x. And this cumulative is just x. And that's just a number 1 there. So when it's uniform, things simplify a lot. Okay? When it's uniform, the density of x, there's that n minus n choose j times j is there. And then it's x to the j minus 1, and 1 minus x, and n minus j, and the density itself is just 1. So that's the density. Can we rewrite this in any way so that it looks like one of the distributions we studied? What's the candidate? Uniform between 0 and 1. Maybe it's a beta. Right. It's x to a power, 1 minus x to a power. usually for a beta, we need, to see it, we need j minus 1, we need a minus 1 there. We want a minus 1 over here, x minus j minus 1. No, plus 1. We want a minus 1 over there, right? So if we change it like that, it looks like the one parameter minus 1 and the other parameter minus 1. And then what we want to see is, do these things work out over here? Well, this combinatorics has n factorial, and then there's a j factorial. J is still there, and then n minus j factorial. But for integers, these things are like these gamma functions. So this was gamma of n plus 1. One of the j's cancel, so it's j minus 1. So it's just j gamma of j. And then gamma of n minus j plus 1. Yeah, it goes up like 1. And then there's next to the j minus 1 and a 1 minus x, n minus j plus 1, minus 1. So that's a beta density. Right? So the jth order statistic from a sample of uniforms has a beta distribution. And so all this work, the jth order statistic is distributed like a beta distribution when the x's were uniform. And the parameters are j and n minus j plus 1. So its expected value is the expected value for that beta. And the expected value of that beta is j over n plus 1. The first parameter over the sum of those next two. So that's the average, if we had 1,000 children and you score them from 0 to 1, and they're uniformly distributed across this thing, and you look at what's the 5th percentile, 5 out of the 5th one out of 1,000. This would be its expected value. This would be the distribution for it, and that's what you would get. So you know the mean variance probabilities of being smaller than a certain amount or bigger than a certain amount in there. And so it could take all the x's, and if you're interested in a certain percentile, a certain order statistic, you have the probability distribution for it. This one is a little bit more, it's more involved in the details because of the combinatoric aspect of it being, some of them less and some of them bigger, right? But we figure out the cumulative distribution function in some way, take the derivative for the density function, and there might be a little manipulation to make it exactly match up to something that we know, but then we get the densities. So we, in simulation, you could do a little comparison, right? You could say, say we're going to do 10 uniforms, and we want our jth order statistic to be, the 20th, the 30th percentile. Right? What's the distribution of the third one, right? Our theory there says that if we take, say, 1,000 samples, let's see, I'll take it from the beta, right? The beta says we should have what? It was a j, right? J, and then j, and then n plus j, n minus j, plus 1, should be what the beta distribution is there, right? And so that's what the density should look like for the third value out of these, right? It's less than halfway, kind of in that area. The other way to do that, right? So we could, it's the same thing as simulating, let's say, simulate 1,000 times, right? And for, b in 1 to 1,000, we're going to say the jth order statistic for that replication is one way to do it. We can take random uniforms. We said n is 10, so we're going to have 10 uniforms between 0 and 1. We're going to sort them in ascending order. Right? And the third order statistic, let's take the third one. Go through that process. Go through that process 1,000 times. What does the histogram of the jth one look like? It looks pretty much like that beta distribution. A little, it's a different sample, so it's a little bit different, but it looks quite similar. Right? The mean of our x beta, I call it a histogram. Back up here. I save that and don't do a histogram yet, right? And then do a histogram of my x betas. It looks kind of the same. The mean of my x betas for that histogram is about 0.27. The mean of my jth values about 0.28. 1,000 samples, there's a little bit of variability there. But the process of once you figure out that it is beta, you don't, that's the result. But any questions, right? So the order statistics, it's kind of interesting on its own because they're very useful in a lot of applications. But in terms of this transformation business, it just emphasizes what's the CDF, what's the CDF of the new variable, the derivative you get densities, and then you can do a little bit of simulation. The homework doesn't particularly have anything on order statistics on it, but a few of the things step you through things with like, you know one variable, what's the CDF of that variable, now let's transform it, what's the new CDF, and differentiate it, so it goes through much the same process. So that's primarily what I wanted to do is maybe show one or two examples, the type of things that's on the homework, right, more explicitly. So for this, and kind of go through the steps, right? Because you follow, I don't know, for B, if I follow certain steps, it's clearer what's going on. So let's say we have a random variable x, and the density for our random variable is 12x squared 1 minus x on 0 between. So it's maybe recognizes this happens to be a beta distribution of e to the 1. And so this is going to be some number between 0 and 1. And then y, let's say it's pi times x squared. Whenever you do a transformation, it's good to think about the range. So that's something that you can do. And in the homework, like one part of the problems usually is figure what is the range of the variable. So if x goes between 0 and 1, right, y is going to go between 0 and pi for its possible values. The cumulative, this is the PDF method. The cumulative distribution function of x, if we want to find that, would be an integral from 0 to x of this density. I'm going to put a t in here in place of that because like always, if that x is up there, just kind of keeps it from getting that much confused. So this is 12t cubed over 3. T squared, so that one's t cubed. There's another 12t to the 4th over 4. It's evaluated from 0 to x. So it's 4x cubed minus 3x to the 4th. Is that right? 12 onto that, yeah. So if we differentiate that, you get 12x squared, 12x cubed. So yes, that works. Right? That's the cumulative. The cumulative distribution for y. Right, we're interested in this variable. So I think for me it's always kind of helpful to write down. Sometimes maybe you can do it in your head. better than I can do it with my head. I always, I like to write down the pi x squared, y. And what we know is the variable x, so we're going to solve for x. Less than or equal to something. So in this case, we'll have to take y over pi, and take the square root of everything. There's no real complication. All values are positive, so there's just a 1-to-1. Square root is 1-to-1. And so if we plug this right, in for these x's, right? That's what this says to do. That's what the cumulative means. The cumulative evaluated at that point means plug that thing in. So it's before, then it'll be y to the 3/2 over pi to the 3/2, and then minus 3. And to the 4th is going to give us y squared over pi squared. Nothing I did particularly mean anything to me that density. That's just what that's just the cumulative is. Right? And if we want the density function, so it's on that scale, we just have to differentiate it. We differentiate this thing with respect to y, then that's our density function. We get 3/2, so that would be, what, 6 over pi to the 3/2, and then it's y to the 1/2. And this one, you differentiate, you get multiplied by 2y over pi squared. If you try to simplify it a little bit to make it look like something new, at least you could pull out a pi 3/2 here out of each one, and a 6 out of each one of those, and you would be left with. I'm going to write it like this: the square root of y you could pull out, and then 1 minus. Y over pi square root of all that. Something like that. Maybe you put a pi back in here, take one of those, so it would look the same. So something kind of like p times 1 minus b, that type of pattern showed up a lot in our things. So not that makes much difference, but y's between 0 and pi, so the y over pi is between 0 and 1, so it kind of looks like it. It resembles the form we would have seen a beta, even though it's not. And that's the density. If you went what was this, PDF route? We figured out the density of y, we figured the density of x at the inverse of evaluated at y, an inverse function, and then this with respect to dy. There's a derivative thing that could be up there. So the density of x, first off, doing it this way, was this 12x squared 1 minus x. And we let y equals pi x squared. Right? So that's the g function, the transformation function. So using with densities, inverting, we solve for x. So x equals y over pi square root. We did that essentially, in this. We had to do that here in the CDF approach. And that's the same inverse as this one. But now we're going to take the derivative of that thing with respect to y. Right, so it's y to the 1/2. And you get 1/2 out front. And then y goes to -1/2, which is like square root, right? Square root 1 over this root. So that ends up being the derivative of that thing. So to do this PDF type of approach, you got the density, your transformation, your inverse, and then you just differentiate it. And then we plug things in. So f of x is 12, and we're going to put in our transformation thing. We're going to put that thing into there. This is the g negative of y term that goes inside. And if you square that, you just get y over pi. But you get 1 minus x, so there's 1 minus the square root of y over pi. Square root of the whole thing. And then this other derivative thing, right? 1/2 the square root of pi times y. And if you simplify that a little bit, it's going to be the thing that you had before. 6 is there. This thing, we pulled out 1 pi. And then we'd have a square root of y over pi left over times the 1 minus y over pi. And that's the density for that random variable. And y, y goes from 0 up to pi over that sigma. So if you wanted to, you can calculate the mean, you can calculate the variance. We can plot it with, it relates to simulation. So let's do a big number of betas. I did that before. I'll just call it x2 for no particular reason. Let's call it our values here w. Well, we call them x over there. I'll just put 2 x's. So it doesn't overwrite the other things there. Those were actually betas. Let's do 1,000 of those things. That particular beta, because x is raised to a 2 power, so it's 3. And the 1 minus x was the 1 power, so it has to be 2. It's a beta of 3, 2. Right? So that's a distribution of x. They're not real small typically, but they're pretty wide. Our y's was pi times x squared. So the y values are like that. They're a little bit more evenly spread out. Is that right? Well, one way we could try to look at that is we could take a sequence of values from 0 up to pi by, say, 0.01. So this is going to be 300 some value, 0 to up there, right? And we can simply plot, right, our sequence of y values versus the density. And we determine that the density is 6 times the square root of y over pi times 1 minus the square root of our y sequence over pi, y value over pi, square root there. That ends that one. Divided by pi. And so let's make it a nice line. So that should look kind of like that curve if things have worked out. Right? Oops. One too many That's what that density function looks like, and here's our simulation of, 1,000 values. It's not dissimilar from it, right? We could maybe do our XX1 up here, and let's make it 10,000 values, right? And then our new Y's is that. So the histogram of YY with 10,000. That's not dissimilar from the actual density curve. 10,000 looks more like that than 1,000 did, right? So that's figuring out the probability density. So if that's important for your random variable, that's what you get there. But any questions about doing those or that process? So, look at the homework as you step through some things that, it kind of goes through steps. So it looks like there's a lot of parts that are trying to do this process and breaking it out. I try to give a few hints along the way that this is the answer we're looking for and so on. And the computing is kind of the code is there to do some of these graphs. And so for this, if you had to decide how does this compare to this graph, right? You might, you can just on your paper make a little sketch, maybe include something about the ranges or something, and some comparison. Sometimes it will, you'll have an original variable and then another variable, and they'll look similar or maybe they'll look quite different. So some comparisons by words or pictures would be fine. Yep.
Is it easy to plot them on the same set of axes in R?
In terms of this versus.
Could you put them both in one picture?
I think you can do some things. You can scale them. So the histogram, you can make it a probability histogram. So then it does it percentages, kind of density, more like density things here. And what was the, this one goes up to about 0.4. So if you do our plot up here, the plot command creates a new picture, but if you do points, it would add it to that. Yeah, there you go. So you can scale them, and it kind of comes up to that. But anyway, so order statistics are kind of an interesting thing. I think mostly we've used it as a mechanism for working with the CDFs versus the PDFs and seeing how that kind of ties into a little of the combinatorial probability that we had in the past. And just thinking about random variables and what does it mean for when you make statements like the maximum has to be less than a value or the minimum has to be bigger than a value. How do you translate that into a few of those things? But I think that's probably good for now. When we come back, we'll look at things, talk a little bit about the bivariate, multivariate things, and what are some of the probability distributions that come out of normal samples.
Here's my project.
Oh,
It's a little bit long,
that's all right.
but it's mostly equations.
Okay.
I think the actual.
Wow, yeah, that's a lot.
Yeah.
You're good at doing this, huh?
Yeah.
Oh, I think that was, wow, cool. All right, that's fine.
Perfect,
Yeah,
thank
have a
you.
good trip.
Thank you.
Yeah.
On Tuesday, I won't be here or traveling. You going to? Well, I also.
You also be traveling, where are you going for this one?
Franklin Piers. Yeah, I don't know, we have game Mondays, we're staying over. Yeah, we're not coming back to Kansas until Wednesday. And then we might miss Tuesday. But we'll get back to
It's
you.
so tough, right.
It is, right? at the
Things
end
will
of
be,
the semester.
posted.
Yeah.
And, if there's sometime you both want to come in, common questions,
Okay.
time together going over it, so.
Thank you. Perfect, thank
Yeah,
you.
sure.
We better watch this.
Budget, yeah.
Yeah, so if we were to do like a tournament kind of style thing, like what, we're not really sure like what we should look at, like specifically. It's like we don't want to make it too broad.
Are we looking at like different outcomes, like different possible like brackets that could have happened?
I mean, you could, and so, what's the, so one question, what would be the probability, say, there were 12 seed would make it to the next round?
Yeah.
Or 2 rounds, or 3 rounds? And that could be kind of a starting point.
Okay.
So that if they have a certain rating, right, relative to their opponent,
Yeah.
and maybe you can turn that into a probability. So one has a power rating of 60 and one has 70. Maybe the chance that one wins is 60 out of 130 if you add those two together, than 170 out of one. So you can kind of get probabilities out of that. And if you have 4 brackets, what's the chance that at least one 12th seed goes on?
Okay.
Could be something like that.
I see what you're saying.
And then what's the chance that they go kind of 2 steps, right? So sometimes something like that, or
So we can kind of just follow like one specific like team or something like that through.
yeah, you could
and,
you
like,
could
go,
you could do
like,
that,
step by step.
right? And then if you can take a question that you're answering for one team and generalize a little bit, right? So if it's this particular 12 seed going through, what would have happened had there been some change, or power ratings been a little bit different, or it might be possible to, if you wanted to take on kind of the computing side, maybe just take one division, like 16 teams, right? So
Okay.
that's smaller than all 4 parts. And if you have this pair of games, have all the first games, and there's probabilities that each team wins.
Yeah.
You go forward, and then the 2 that come out of there, you compare their probabilities and see who comes forward. And then you would get kind of a probability that any one of those teams, like does the first seed get through, does the second seed?
Oh, so kind of like a simulation.
Kind of a simulation, yeah, that could be.
Okay.
I mean, it's you could contrast that to what if things are equal, right? What if it's 50-50 for each game, right? Then the chance that a 12th seed comes through is 50%, 50%, 50%, and so on. And that probably looks a lot different than the real simulation if those probabilities are pretty different.
Okay.
So I think, kind of describing this structure, maybe there's probabilities, so what's the probabilities of a single game winner? And then what's a 2-step thing, right? And then kind of take it from there.
Okay. I understand. Thank you.
Sure. Yeah.
Have a good break.
You too. Happy Easter.
So, all right, I've talked about local projects.
Yes.
There's this project in here,
Uh-huh.
kind of similar to them, but I wanted to do hockey.
Okay.
So like to get
Best
the
of
same
7, yeah.
yeah. So it'd be like the best of 7 game series.
Yeah.
And I was gonna try to compare like going in before the games, and I would use the odds, like the Vegas odds that they use before the games, and then before the series starts, and then kind of use those same odds through say the games, and then I would adjust the odds per game based on stuff after, and kind of compare the two and how.
Yeah,
that
so
would be.
if you just had the accuracy at the beginning versus do they update the odds and
After
regs
each
and
game
things
and
like that,
stuff,
So part of it could be just the description of going from odds to probabilities.
Okay.
In that, and how much does that deviate from 50-50,
Yeah.
right?
Right.
How much of a difference does it make?
Because the upsets this year in the Stanley Cup have been insane.
Yeah.
I know, it's Tampa Bay out in the first round,
Yeah.
Penguins out in the first round. I was going to do that for this class. And then for the other class, I did this.
Uh-huh.
I took, in my stats econ class, I did a project, and I wanted to reuse this same data that I have,
Okay.
because it's
It's a lot, yeah.
it's 600 and
Okay, yeah. Yeah.
87
Right.
worth.
Yeah.
And for this project, I wanted to compare how much. I basically wanted to see if being an athlete in college, how earnings out of college and stuff.
Okay.
But I have so much more data between GPA, their majors,
Right.
their year of graduation, male, female, age bracket ranges,
Okay.
and I kind of wanted to play with some data.
Yeah.
And I was just asking if I can reuse this.
Or you can reuse the
recording.
data
Yeah.
set, yeah, because
Okay.
you might have to do some coding
Yeah.
to get it into levels. or-
Yeah. Yeah, and I was also wondering, like, how exactly should I go about, because I did these in ranges, like, how exactly could I, like,
Well, to do, I mean, it's not perfect, but you could put the midpoint for some of those.
yeah,
If you thought it was kind of even, kind of just taking the midpoints.
of the age range?
Yeah,
and
particularly,
the
you know, 20,
earnings?
yeah, and earnings, yeah, you get something like the 150,000 or above, though, you know, maybe
Yeah.
peg that at 200,000.
Yeah, all right.
So yeah, there's a lot of potential for that. So there's a coding issue and making it work. You wouldn't necessarily have to do every single comparison, but with this, you know, there's male, female.
Mhm.
If you keep it just as age ranges, then you have categories.
Mhm.
And so that'd be analysis
Technically,
variance.
yeah, okay.
So, you know, 3 or 4, you know, different groups, average income, maybe code this, you know, average GPAs, and GPAs look like they're in ranges too. So
Yeah.
you might just do midpoints and.
Yeah, yeah, I kind of.
Yeah, so comparing, if you did something where you compared 2 groups, and if you did an ANOVA, comparing some numerical outcome.
Mhm.
Another way is correlation or regression.
Right,
So there's a lot of potential.
okay, cool.
I would suggest, you know, trying to code one thing.
Okay.
You know, think about, I'm gonna try to do a regression, or I'm gonna try to do a t-test or a ANOVA.
Mhm.
I'm gonna code the couple variables that I need to make that work.
Like,
Go ahead.
small scale first.
Yeah,
Yeah.
rather than try to recode every single variable at first.
Yeah.
Code the couple that you need for an analysis,
And
and then get that analysis run, write up some summaries of that, kind of get incrementally.
Okay.
Because if it goes well, you know, you code a third variable, you get a different analysis, and maybe you can even get a third analysis, but
Mhm.
without doing more variables.
Okay.
So I think,
Yeah, I kind of want to run a regression between age, sex. I don't know how I would measure major, but I want to run it between age, sex, income, and GPA.
you know, the majors, there's so many categories, but, you know, would one be more quantitative?
Right.
You do sciences, non-sciences, and you could have a variable that's 1 or
That's,
0.
yeah. Actually, that's a good idea.
Yeah, or there's, you know, once you get multiple levels, so in R, you can put factors.
Mhm.
So you could, majors is probably a lot of different categories.
Well,
Put
yeah,
in there
I was
all at
thinking
once.
do
You can do
'cause-
like quantitative or, you know, maybe science.
Yeah, so I'd do like bachelor's of science, which would include econ with all the sciences
Uh-huh.
versus I think math. Is it math of science
Yeah,
too?
yeah.
And then everything else.
Yep.
And I think.
And see
pretty-
if see a difference there.
Yeah, I think you definitely.
Yeah.
Is business isn't though,
I don't think business probably is.
but yeah, I could end up doing something like that.
Right, I mean, it becomes kind of a question of which one should be included in that.
Yeah,
versus
and even
not.
I can even split that even more and go, say, math in the traditional sciences versus a business econ versus
Right.
basketball or something, whatever. Another
Yeah,
one.
and so taking, you know, the kind of incremental approach, where if you just do a regression based on GPA
Mhm.
and income, or maybe age and income,
Mhm.
and just do a simple regression first. So you code 2 variables, run a simple regression, get it written up
Okay.
in there, and then if it's, depending on time you have, and the ease of coding some of these things,
Mhm.
some things that.
Take it from there.
Yeah, take it from there.
Okay. Yeah, I'm getting my wisdom teeth out tomorrow.
Oh,
I'm going home right now. So this
well,
will be-
that's it, yeah, have a good time with that.
Thank you. But yeah, it'll definitely be on the couch for the next couple days.
Yeah.
Don't know what state I'll be in though. We'll see.
One daughter about ready to get braces off, and the other one getting put on, so.
I just reuse them.
Just reuse them.
Tell her you're reusing them.
Well, she has a little biplane, and they say, what color do you want? She said, rainbow. It's like, oh,
Great.
that's not a choice.
Thank you. Have a great
See
Easter
you.
break.
Thanks.